Hi, good afternoon, everyone. So this is week 10. Today we will discuss some algebra problem and a little bit about counting or probability. So we will first review some very basic algebra. Here is the difference of square formula, and this is so important that everybody should be able to write down this either from the left to the right or from right to the left at easy. So from the left to the right, we see that we are multiplying two binomial algebraic expressions, and the result is a difference square. So a plus b times a minus b. This is so fundamental. The result is a squared minus b squared. If we go from the right to the left, this is called factorization of this polynomial a squared minus b squared. So this is so fundamental. Everybody should firmly understand why this is true and use this formula in both directions just as easy. So it will have very broad applications. So let's take a look at our first problem. This is problem number 6 from meeting number 20. Given the square of 55,555 is this huge number, find the square of the next integer, 55556. So apparently you were provided with a known result and want to get this the square of the next number. So you really want to use the information that's given to you, right? We already get the square of this 55555. And what's the square of the next number? How to make the connection between what is known and what is unknown. Well, that's quite obvious, because if you want to evaluate, say, 55556 square, and you already know the square of the number that is immediately before it. So how do we make the connection between the two? Obviously, you want to write this number 555556 as 555555 plus 1, right? And then, well, in this case, you will be able to use another formula. This is a binomial square, which is also very fundamental. If you write this, you should immediately know this is a squared plus 2ab plus b squared. Let's make it very clear. Okay, so this is also another important formula, and from the left to the right, we are expanding this. From the right to the left, we're factorizing this. So with that, we will be able to write this as 55555 squared, which is a squared. And the reason we are doing this is exactly because we want to use this formula so that we can expand it and write this into what we have on the right, so that the a squared term, which is already provided to you, can be directly used. So therefore, here is a squared times 2 times this a, which is 55555, then plus 1 squared, which is of course 1. Now you see why we are doing this, because this already provides to you, right, what number that is. Wow, that's a big number. So whatever number that is. 58025. 58025. That's the square of this guy. This is already computed for you. So all we need is add the last two terms, which is quite easy. 2 times 555, we know that is 0, 1, 1, 1, 1, 1, 1. 5 ones, right? And 1 is just 1. Now, this is super easy because you can actually further combine the 1. So replace that with 1 so that you simply add how many? This is, I think I wrote one more 1. Yeah, should be 6. Yeah, because this should be 5, 1, then 1, 0, then plus 1 is 1. So you just add this number to this number. So you add each of the last 6 digits by 1. Fortunately, there's no 9 there, so you don't have to do any carrying. So that's just this number. So 5 becomes 6, 8 becomes 9, 0 becomes 1, 3, 6. So this is a very easy problem, but the process of your analysis is what you want to learn, because you already get this 5555 square. So in order to get 55556 square, you want to use what you already have. So you want to write the letter as in terms of the former. So you add that 1, and at that point you can use this binomial square formula. Okay, so that's this problem. The second problem, number 8 of mini 20. Okay, suppose A, B, C are consecutive positive odd integers. So that's a lot of words. Consecutive positive odd integers. You immediately should kind of understand what this statement means. Of course, without lots of generality, it says C is greater than B and greater than A. So what that means is that, say, you have 3 consecutive integers, but they have to be odd. So like 21, 23, 25, and this would be your C, this would be B, and this would be A, because C is the largest. So you just think about something like that, okay? So now you were told B squared minus A squared, the second largest square minus the square of the smallest is 344. So what is the C squared minus B squared? So this is really something not that difficult. We can write this in some very clever way. Let's just say we write a B. In this case, you may not need to, but in general, it's a good idea to do exactly what the problem tells you. They are all odd integers, right? How do we represent an odd integer? Well, we usually represent an odd integer as 2k plus 1, where k is integer. This guarantees that this number would be an odd integer. And positive, then you just need to k to be at least 0. So if k is at least 0, then 2k plus 1 is guaranteed to be a positive odd integer. Also here there's a little bit more, because b is greater than a. A also has to be positive odd integer. So k actually needs to be a little bit bigger. But we don't really care about this. So we just write b as 2k plus 1. If that's the case, what is a? A is the smaller than immediate previous odd integer, so it has to be 2k minus 1. And what is c? Well, c has to be 2k plus 3, right? That's how you represent it. In this case, you did not lose any information. Alternatively, we will see if we just say b is x, or just b, then the c will be written as b plus 2, a would be b minus 2. This is okay representation, but it does not guarantee that b is odd integer. Okay, so we will see whether that's a really big deal. So let's work on this case. What do we have? We have b squared minus a squared equals to 344, I believe. Yes. So if that's the case, you just do whatever you need to do. Because we represent b as a 2k plus 1, so this is just 2k plus 1 squared minus 2k minus 1 squared. Do we really need to expand both, then do the summing them together? What I mean is that we can use binomial square to expand this and expand this as well, and then do it. Of course, you can do that, but in this specific case, we have a better way. That is using the binomial, the difference of square formula we talked about earlier, right? Let me use green to remind you. B squared minus a squared, or I should use x and y just to avoid reusing the same symbols. So x squared minus y squared equals to x plus y times x minus y. That's what we reviewed at the very beginning. So you think this whole thing as x and 2k minus 1 as y, so we can use that formula directly to avoid using binomial expansion. So if that's the case, this would simply be x plus y. That's 2k plus 1 plus 2k minus 1. Plus 1 minus 1 canceling out each other. So that's simply 4k. The second one is 2k plus 1 minus 2k plus 1 minus 2k minus 1. You should be very good in basic algebra. You immediately recognize that without writing it on paper, you recognize that's it too. Okay? So, meaning that what I mean is that in your mind, you should know this. Minus 2k minus 1. Because in this case, what you really need to do is just canceling out 2k minus 2k, they're gone. 1 minus a minus 1 there. So negative become positive, so this is really 1 plus 1 equals to 2. So what I'm saying is that this should happen in your mind really just handily, so that you can save a few seconds. If you really do everything on the paper, you can do that, but Mathcounts really require you to compute everything very fast. So how will you train yourself to do this? Do a lot of exercises. Do a lot of basic algebra polynomial manipulation so that all those fundamental things can happen in your mind very quickly and very accurately. If you do it very fast, but you all gather the results wrong, that's completely useless, right? So you have to be able to process such basic computing in your mind fast and accurate. So this is just the plus of the 2 is 4k, the difference is 2, so this is really just 8k. And we were told that this is just 344, so we immediately have a equation here. Why we are doing this? Because we want to get a k, so that this is not our goal to get it. So we do perform this step because this is the condition that we know. We use this as a stepping stone to solve what we really want to solve. That is c squared minus b squared. That's what we need to compute. So c squared minus b squared, but because we represent c as this one and this one, we can write that in terms of 2k plus 3 squared. So at that point, we may be able to need k. But hold on for a second. We can do this a little bit later. You already get there. We will need to see whether we can use this directly or we can solve k now. It's not difficult to solve. K equals to divide 344 by 8. That should give us 43, right? Again, this can also be performed in your mind. How do I divide this? 34 divided by 8, you get 32, that's a 4. That's a remainder 2, that's 24. 24 divided by 8, that's 3. So you get 43. But hold on to a second to see what happened. So we want to compute c squared minus b squared. We know c is this. So this is 2k plus 3 squared minus b squared. That will be 2k plus 1 squared. Again, just like in this step, we don't need to expand both by the binomial square. We directly use the difference of square formula. So 2k plus 3 plus 2k plus 1, that's 4k plus 4. This should happen in your mind very quickly, okay? So, and 2k plus 3 minus 2k plus 1 as a whole, that should also happen in your mind very quickly. That is just 2, right? 2k plus 3 subtracting 2k plus 1 as a whole, obviously the difference between them is just 2. Now you see why we just say hold on to that. Because 4k plus 4 times 2, that's just 8k plus a. That's all you need to do. We already got 8k equals to 344. So actually at this point you can see that you don't even need to solve k. Because even if you solve k, you still need to multiply that by 8. That's completely a wasted step. You need to get 8k anyway, and that is already available in our intermediate stepping stone step. So you can simply just directly use that and get this is 352. Okay, so that's what you need. So the point here is that sometimes lazy is good. Procrastination has some merit because in this step you need a k anyway. So you may ask, how do I know I will use a k, not just k? What if here is 9k? If this is indeed 9k, you cannot use this. You have to compute k first, then plug in, multiply that by 9. How do we know that we will actually use ak directly rather than k? Well, this is more like art rather than science because we observe what we did earlier. We know square the difference. If you are really good at algebra, you should be able to feel that the difference of square between those two are kind of similar to this one, meaning that all the terms about k should be very comparable. The difference should be more like in terms of constants. Therefore, based on this kind of direct feeling, you may want to hold on to solving k until later when it's really necessary. And as it turned out, in this case, it's not necessary to solve k directly. So now back to our earlier question. If we represent the three numbers just in terms of b minus 2 and b plus 2, will that work? Actually, we can try that, right? So b squared minus a squared, because we know a is just b minus 2. So that's just b squared minus b minus 2 squared. And this is simply do what we just did. B plus b minus 2. That's 2b minus 2 times 2, because b minus 2 as a whole gives us 2. So this is 4b minus 4. And this is 344. Okay? Again, in this case, we may just keep it there. We don't solve b right now. Do the c part. C squared minus b squared. We know c is b plus 2. So this is b plus 2 squared minus b squared. This is simply 2b plus 2 times 2, which is 4b plus 4. Now we immediately see that we already get 4b minus 4. Now we need to get 4b plus 4, so we simply plus a to this. This should give us 4b plus 4. And that's exactly what we did earlier here. So you can see that in this specific problem, the information that the 3 are consecutive odd numbers, that's kind of oversupply of the information. Whether it's odd number or even number doesn't really matter. All we need is to know the 3 numbers are equally spaced. And if that space is 2, you will get the same result regardless. So we did not actually use the fact that the now 3 numbers are odd numbers. If they're kind of generally represented b minus 2, b plus 2, we still get the same result anyway. And of course, as it turned out, in this case, if we solve the b with k, you will still see that b will be, for example, here, if you get 4b minus 4 equals to 344, then b would be 348 divided by 4, that would be 87. Okay? Indeed, b is an odd number. It's just that we did not use this fact in our solving of the algebra. Okay? So this problem, although we spend a lot of time, we just want to illustrate the basic process of your algebraic thinking. The problem is much easier than it appears. You just need to know how to derive the relationship that you need to solve from other conditions that are available to us. Okay? So let's work on the next problem. Okay, find all pairs of positive integers m and n such that a squared is 105 greater than n squared. So what does this problem ask us to do? Well, you need to find certain m and n which meet a certain condition. And what is that condition? M squared is 105 greater than n squared. So you immediately write down that condition. But this is not something that is good for us. So we really want to manipulate. So it's not difficult. You want to write this relationship in this in this way, right? M squared minus n squared equal to 105. Why? Because now we can factorize this thing. Because this is different of square, so we immediately see this is m plus n times m minus n equal to 105. Now we see what we need to do. Because we were told m and n both need to be positive integers. And we need to find all possible combinations of mm, all pairs of positive integers mn. If they are both integers, m plus n must be integer. And without the loss of generality, one of them must be one bigger than the other because we don't really know which one is m, which one is n. So we can safely assume m is bigger than n, so this will be positive. So that means that we just need to figure out all the possible decomposition of 105 into the product of two positive integers, right? We don't need to do complete factorization of 105. If we do it, that's not difficult. Actually, it's very straightforward. 105 is just 3 times 5 times 7. But because we need to 2, so we just need to break down 105 into a product of two integers and investigate all the possible ways, right? So 1 times 105, that's the very obvious one, but people tend to forget this in the first place because it's so trivial. It's just 1 times 105. Then you have 3. We will write down the second one accordingly, but Why don't we just list all the factors? You have 3, you have 5, you have 7, but you also have 3 times 5, that's 15. 3 times 7, that's 21, and 5 times 7, that's 35, and finally, you have all the 3 multiplied together, that's 105. Did we exhaust all this? Well, you have to understand there's a formula which will tell you how many factors you have for integer. Does anybody still remember that formula? If you have a prime factorization of an integer, you break it down into something like this. They could have some power, but in this case, we don't have power, so it's just power is 1. How many factors or divisors 105 have in total? The formula is 1 plus 1 times 1 plus 1 times 1 plus 1. And the general formula is that whatever component you have here, let's just say exponent 1, exponent 2, exponent 3, the general formula is just e1 plus 1, e2 plus 2 in this case, plus 1, I'm sorry, times e3 plus 1. You just add a 1 to each exponent and multiply them together. And we explained this in accounting class, I believe, but just quick reminder, why are we doing that? Because essentially we just need to see how many different ways we can generate a factor. Any factor of this integer must come from some combination of each individual prime factors. And for each individual prime factor, we have exponent plus 1 way of choosing how many copies of this prime factor that will contribute to the factor. Because 0 component exponent is also a choice, because 3 to the 0 power, that's just 1, meaning that there's no contribution from 3 at all. On the other hand, if this is subject to 5th power of 3, so essentially you can choose how many copies of 3. You can have 0 copy, 1 copy, 2 copy, all the way through 5 copy. All those cases can be can make a contribution to the factors that you try to build. So each of the prime factors will have this many possibilities. And when you combine all of them together, that gives you the total number of factors. So in this case, we know it's 1 plus 1 times 1 plus 1. So we know with confidence that there are 8 factors of 105. And here we have exhaust all of them. Okay? So 1, 3, 5, 7, 15, 21, 35, 105. Perfect. We exhaust every possible factors, not just prime factors, because some of them not prime, all the factors of 105. So with that write down, you can see, you can write down the other one easily. This would be 35, this would be 21, this would be 15, and this should be 7, this should be 5, this should be 3, and finally this should be 1. Why are we doing this? Because each such a pair, let's just say 7 times 15, must match this relationship. So one is the larger one is the smaller one. So in this case, that means that m plus n equals to the larger one is 15, and minus n equals to 7. We know how to solve a system of equation like this. We know the sum of 2 integers, we know difference of 2 integers, so m is just the average of the 2 numbers, and n is just the difference between the 2 values and then divided by 2. And this is fundamental algebra. Everybody should be compute this super fast. You must understand why we are doing this, right? You just add up to the left-hand side, divided by 2, that gives you m. If you subtract this guy from this guy, you get 2n. Again, you have to divide it by 2. So this is really fundamental. But the point is that each such pair will give you a solution like this. However, you have to be a little bit careful. Depending on how the problem is asking, you will have to consider, say, 7 times 15 and 15 times 7. Essentially, they will give you the same set of 2 numbers, but the mn relationship is different. In other words, let's take a look at this example. In this example, m equals to 22 divided by 2, that's 11. N is 8 divided by 2, that's 4. So m equals to 11, n equals to 4. But if you try this one, because now mn reverse their relationship, so you will get the same thing, but exactly the same number. Because even so, you get a different pair, but you are just looking at which is the larger number. That's still 15, right? So m plus n is still 15. M minus n is still 7. So even when you write down this, in terms of mn, it did not change. But in this case, do we need to reverse the m and n? No, we cannot. We know m is larger than n. It's not like something, say, m and n can be reversed. We cannot. So therefore, although we have 8 pairs here, only 4 of them are actually unique. For example, 1 times 105 and 105 times 1 will give us essentially the same m and n. Okay? So therefore, the answer is that we only have 4 pairs. So we only need to consider the first 4, because the last 4 essentially still the same thing. You see that? Maybe I use a blue pen. So if you look at this 7531, that's exactly what you have here. So although you have 8 pairs, but 4 of them will give you the same m and n. That's the point. Okay? So solve this problem is not that difficult. You just go through each one of them, but you have to do this very quickly. We explain it in a kind of lengthy way, but when you do this problem, actually you should do it very fast. You're not supposed to spend more than 2 minutes on this. Okay? If you are really good, perhaps you can finish this under 1 minute. Super fast. Okay. But that's what it is. All right. Next problem. What is sum of the digits of 29999 square? Well, how do we do that? Well, you look at this weird number. You probably know what you should do, right? You don't want to compute the square of this number. You want to compute a very convenient number, and that has to be, how many nines we got here? 1, 2, 3, 4. We get 7, 9, 8 digits in total. So this has to be 3 and then 0 to 7 zeros. So you want 1, 2, 3, 4, 5, 6, 7 minus 1, because that's the same thing, and the square. That's the thing you want to compute, because that's exactly what this is. Well, we are not just to compute this number itself. We want to sum all the digits. But we know when we have that many zeros, that should eventually we should have something that's really convenient to compute. So what is this? This is 3 times, actually we should write it in the so-called scientific representation, right? This should be 3 times 10 to the 7th power. This is this number, just remember. So we have to take a square. and minus now 2 times this. This will be 6. So this. Everybody understand what I'm doing? Minus 2ab. A is just this one. B is 1, so we can ignore B. And 2 times that, 2ab. 3 times 2 is 6, so this is 1, then plus 1. Okay, now you see that this one is just 9 times 10 to the 14th power, subtracting 2 times this one plus 1. Okay, so this is a little bit tricky because we were asked to compute the sum of all the digits, so we still need to be very careful, write this down. What is this? So essentially we start with this number. This is 9, and you have 14 zeros right there. Okay, then you need to subtract this number. So because this number has 7 digits, so we say that just we have break 14 digits into 2 portions. We have a first group 7 digits, and the second group another 7 digits. Because when we do this subtracting thing, we will align the last 7 digits. We are trying to work with the 8th digit. This is the 8th. And we are subtracting a 6 something from here, right? So just do that. So you will immediately see that when we do this, the last 7 digits won't change. We will have 7. And when we do this, this becomes 10 minus 6. That will give us 4. Then everything else becomes 9. And 9, 9, 9, 9, 9. How many 9s? It must be 6. Because including this one, we have 7 zeros. 6, 9. And then this 9 will becomes 8. Because we have borrowing at every digit from that point on. And at this step, nothing changed to the last 7 digits. They're all 0, but don't forget we have to add 1, so this becomes 1. Now we know this weird number. It's a very large number, but it's not that difficult to do all the counting here because we know every single digit. We have 1 here, we have 6, 9 here. So it's 8, oops. We have 8. We have 6 9s, that's 6 times 9. We have a 4 right here. We have 1. Okay? 8 plus 4 plus 1, that's 13. 13 plus 6 times 9, that's 54. And this is 6, 7. Okay? So this problem is not that difficult, but it's really just a simple test of your knowledge about how to compute this. And even without any competition math experience, you should feel that you don't want to do something directly like this. You want to do smart things. This is just one short of a very nice number. That's 3 times 10 to the power of 7. All the zeros, you certainly want to represent 29999 and 30000 subtracting 1. Then use the binomial square formula to expand this one to this one, right? And the rest is just straightforward. Okay, that's what we have for this problem. All right, let's see. Oh, first of all, stay calm. When you see something that really looks very annoying, very complicated, usually it won't be that complicated. That's the first thing you should convince yourself. There must be some easy cancellation. Cannot be possible that you need to do all those computing just, in a hardcore way. So what is the structure here? We have, in both the numerator and denominator, we have many terms multiplied together, but each term is a difference of square. So obviously you want to do cancellation. Can we cancel any of them directly? just take a look. Nothing in the numerator is in common with the contributing terms in the denominator. So we cannot cancel anything directly. However, because each individual term is a difference of square, we can definitely factorize each term in either the denominator or the numerator. But before doing that, we want to pause for a second to see, just to observe what will happen. That will give you some confidence when you do that, right? You don't want to blindly jump into the hot water without knowing what you are doing. So the structure is that we start with two very large numbers. 1998 squared subtracting 1996. The next one is 1998 squared subtracting 1995. So the bigger number does not change. It's always 1998. But the second number is shrinking. So 1996, 1995, all the way to 0. That's in the numerator. The denominator, very similar, except that we don't have 1998, we only have 1997, right? But just think about it. When you do this, you will be able to somehow align them. 1998 subtract 1996, it's very similar to 1997 subtracting to 1995 because the difference is just 2. Right? So now you see, at least after factorizing those two, you will be able to cancel at least their differences, because the differences in the numerator is 2, and in the denominator is again 2. Don't worry about the other terms. So why don't we do that? So, but you need to do this very carefully, okay? So let's just do the numerator first. What is numerator? The first term, 1998 squared minus 1996 squared. So that is difference of square. You break that down as 1998 plus 1996 times 2. The difference is 2. The second one is 1998 plus 1995. This one times 3. Right? The difference now, we know how to do this. Now you continue this process until you have 1998 plus 1 times 1997. Then you have the last 2. This is second to last. We just wrap around a little bit times 1998 plus 0, which is 1998, but we write it in a consistent way. Okay? So, of course, you may want to regroup it, but you want to hold on that for now. What is in the denominator? Very similar thing, just one less. You replace all the 1998 with 1997. So 1997 plus 1996 times 2 times 1997 plus 1995 times 2. In this case, this case is start with 1. I'm sorry, this one is difference 1, right? Times this times 2. Now you continue until you hit 1997 plus 1 times 1996. Then finally you have 1997 plus 0, that is just itself, times 1997. Now if you take a look, if you think about those things, what do you have? You have 2 times 3 times 4 times 1997 until you times 1998. But what do you have in the bottom? You have 1 times 2 times 3. So there are just one less. You still have the same number of terms, but each one is less than the corresponding term in the top, in the numerator. But if you think about it, you just shift it a little bit, then this 2 will match this 2, 3 will match 3, and this 1997 will match this one. So they got all canceled out. So in the top, only this copy remains. And in the bottom, this copy, the smallest copy, remains. Because you shift it, right? In order to cancel all the others. That's beautiful. So that means that we immediately know the contribution from Rho's terms in terms of both the numerator and denominator is nothing but the 1998 over 1. That's the net result for Rho's terms. All the others got cancelled. Now you have to worry about this thing. But you see that this is also of a very similar structure because the first number doesn't change, only changes the second number. So that means that this is just decreasing, right? Yes, this one, 1998 plus 1996, is 1 larger than this one. But from that point on, both are shrinking 1 at a time. So this time, 1998 plus 1995 is exactly 1997 plus 1996. So this is again, there. If we shift it in another direction, we get this one and this one will all matched up. And the last one, you can see that right here and right here. This one is 1998 will match exactly this 1997 plus 1 because you shifted it in the other direction. So the last term here will get cancelled by the second to the last term in the denominator. So all rows will also get cancelled. That means that for these portions of the terms, in the top, this one will survive. And in the bottom, this one will survive, right? It's very similar to what we just did, but in a different way. So that means that the net effect of all those terms after all the cancellation is that in the top, you have 1998 plus 1996 surviving. And in the bottom, you have this last term. Because remember now the shifting is in the direct. The first canceling is that we match up in that way. The second time we match in that way. So that's why here the last term survived. So that means that the net effect of this round of cancellation is that in the bottom, 1997 survived. Now this is very easy to do. 1998 plus 1996 is actually twice of 1997. Everybody should understand that. They differ by 2. Their sum is just 2 copies of the middle. Or their average is the same as 1997. Either way, this gives you 2. Okay, so the final answer to this is just 1998 times 2. And that should give you 3996. Okay? Yes, this looks kind of complicated, but actually it's not. You just need to be very calm, don't panic, and very careful each step of the way. You know exactly what you're doing, and don't get messed up. If you mess up with the algebra, things can easily go wild. But don't, because it's not that hard. You just stay calm, do all the algebra, all the arithmetic carefully, you will be fine. And remain very confident that a lot of those bizarre terms will disappear, will vanish, because there must be a lot of cancellation helping you. Indeed, they're there. Okay? So that's this problem. All right. Now we are entering mini number 24, which having several probability problems. The first one is quite interesting. There are 11 students in Miss McGee's chemistry class. You all love chemistry, don't you? Oh, you haven't learned any chemistry. Oh, that's fine. You will. Okay. In Miss McGee's class, chemistry class, there are 11 students. They're triplet, Baker triplet ABC. Anika, Billy, Catherine. All right. So the teacher called all those 11 students in random order and tell each student his or her final grade. What is the probability that Billy is the first of the triplets that Miss McGee will call? So let's consider this. All the 11 students will be called. So essentially, there's an order of the 11 students. But what we are interested in is the relative order among those 3 Baker triplets. We don't even care about all the other A students. Whether they are called Trump or Biden, we don't care. We just ignore them. So, what is essentially this problem? You have 3 guys, A, B, C. Their relative order is random. And you want to see, out of all those possible cases, what is the probability that B is the very first one among the 3? So you really need to read the problem and understand what is being asked. If you understand the problem wrong, of course you will get it wrong. What is the probability B is first? A clever way would be immediately, is there any difference between A and B in terms of who will get first? No. So A and B must have equal probability. But so is C. There's no difference. We don't say A will get a priority. Everything is random. So among the 3, each one will have an equal opportunity guaranteed by our Constitution, Amendment 14th Amendment, equal protection, right? No, I'm just joking. This has nothing to do with law. But mathematically, each of those 3 must have the same chance or same probability of being first called among those 3. I mean, we only care about relative order among those 3. Even they all are at the very end or at the very beginning of the 11, we don't really care. So each one must have 1/3 probability. But if you really want to, say, do the hard work, how many orders you can arrange those 3? Everybody should understand the formula. That's 3 factorial, right? You have 3. This is the permutation problem. The first one, you have 3 choices A, B, C. Either one can be, any of those 3 can be the first one. And after that, you have 2 remaining. So it's 3 times 2. And then finally, the last one has no choice, must be 1. So you have 3 factorial equals to 6 possible ways of arranging them. Out of the 3, how many of them will have B first? Yeah, let's just say B is first. If B is first, you only have A and C, so that's 2 factorial. Okay? But you only have 1 B here, so this is 2. 2 divided by 6. 6 total case, 2 of them with B at the beginning. But this is not surprising because if you put A here, it also has 2. C here also has 2. And the 3 2's must add up to 6. This is essentially a verification that our initial argument must be correct because each one can be A, B, C, and they only can have 2 cases for each. So it's 2 over 6. That's essentially the same as 1 over 3. Okay. All right. number 1 through 8 are arranged, the problem didn't say randomly, but you should assume that's the case. So the problem, the wording is a little bit off. To be a good problem, it should say arrange randomly to form a 8-digit number. But it also tells you which is a multiple of 5. So although it's random, this is a conditional probability actually, which already determined that this is a multiple of 5. So we only look at those arrangements where the last digit is 5. You should understand that, right? When the number is a multiple of 5, the unit digit must be either 0 or 5. Only in those two cases you have multiple of 5. So essentially, you are told the last digit is 5. In this case, what is the probability that the number is greater than 60 million? This is not a hard problem. The argument is very simple. So we have a digit. What is 6 million? Let's write it down. 6 million is 6 with how many zeros? 1, 2, 3, 4. 6 million must be 70. And that's right. We have 8 digits, right? So 70, that gives us 6 million. We already know our last digit must be 5. And the other 7 digits occupy the first 7 digits, but this number must be greater than 60 million. That means the very first digit should be 6 or 7 or 8. Any of those 3 will guarantee the number will be greater than 60 million. On the other hand, any number smaller, you will fail. Right? 5 we cannot take. So the next largest one will be 4. Of course, 4 something is less than 6 something. So we just, essentially this problem say, what is the probability that the first digit will be either 6, 7, or 8? All those 3 will work. But because it's random, for this first digit, how many possibilities? Other than 5, every digit is possible. So out of 7, you must have those 3 cases that can meet this condition. So the probability is simply 3 over 7. Okay, this is of course a very straightforward one. You just need to understand how to translate the problem as it's asked to the real mathematical statement. Okay, essentially this is what is the probability that the first digit is one of 6, 7, 8? One of those 3. Of course, probability 3 over 7. Oops, our last problem, well, this is a tremendously more time-consuming problem, but since you already watched the video, the key actually to this problem is to understand what we are trying to do here. We have such a weird shape, it's called tetromino. I don't know what the heck that means, but it's just kind of, a name for this particular shape. Okay, tetromino, whatever. We want to cover this T-shaped 4 square shape onto this 3 by 4 or 4 by 3, depending on which one you want to go. Probably this should be named 4, the rows and the column 4 by 3 grid. It can cover this with 4 of them, right? So in a variety of ways. Each time, whenever say it cover 1, 2, 3, 5, the covered numbers, you have a sum. Okay? And it won't give you all the covered cases. You want to add the sum of the sums. Because each coverage gives you a sum, and you figure out how many ways to cover this 4 by 3 grid. And each of those coverage has a sum, you want to add all of them. So it's a sum of the sums. So we will use exactly the same technique in the video. And what is that technique? Essentially, it's something like this. You want to get a sum, which is sum 1 plus sum 2, maybe we use underscore, plus blah 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 blah, plus sum n. You have n totals, right? But each one is 4 numbers because we have a T-shape. It depends on where you go, you have this one. So each one is something like A1 plus A2. Maybe we should use different one. So A1 plus B1 plus C1 plus D1. That represents 4. So let's just say sum underscore n is am plus bm plus cm plus dm. Essentially, we say this is A, this is B, this is C, this is D. Okay? Whenever it has a coverage, say any coverage like 2 or number n, we look at the specific values associated with A and B and C and D in the grid. We call that AM, BN, C, and DN for the nth coverage. We are trying to add rows up. So it's just a different grouping, right? We group this plus A1, A2 plus B2 plus C2 plus D2. That's how you group them. But with the associative law and the commutative law, we can regroup them. Instead of grouping by the orders of the coverage, we can group all the A cases. Essentially, we will have 4 big grouping. The first grouping is plus all the A1 plus A2 plus AN, and B1 plus B2 plus BM, plus C1 plus C2 plus Cn plus D1 plus D2 plus Dn. Does that make sense? That is one way of looking at this. This will give you the same result. But another way is look at the rows 12 grid to see, say, let's say number 1. This is a different thinking, but following the same spirit. We just need to see how many different ways we can add them up. We take a different combination or different grouping of all those numbers. Without any doubt, if you have n coverage, the total numbers they need to add up is 4 times n. We have 4 n numbers to add up. And we just demonstrated 2 ways of grouping them. The first way is by each natural coverage. The second way is just look, if we think that we fix that, wherever this number go, we group these numbers corresponding one. However, we don't have to do that. We can have yet another way of grouping, and that is based on, we take a look at those 12 numbers, or 12 positions to be exact, to see for each position how many different ways this position will be covered, right? So essentially the problem is like this. You have 40 numbers. They are all associated with your different coverage. You just figure out a way to group those 40 numbers into subgroups and then add them up. For the first approach, this is time consuming because we cannot easily track all the possible positions. We don't even know how many. The second one is equally bad. Essentially, the same fundamental problem as the first grouping. However, the technique in the video and the one we'll follow here is take a different grouping based on all those 12 positions. Say this position 2, how many times this 2 will be covered? That's the same thing. So essentially we break it down those 40 numbers into 12 groups. And each group is based on a particular cell in the 4 times 3 grid. That particular cell, how many times this cell will be covered by all those coverages. In that way, we don't even need to know what n is. We just look how many ways, how many times, how many ways this cell will be covered. That's much easier to do for this problem, okay? So you need to just be very clever. So we first understand what the video solution is doing, and logically that means what, and that's what we are doing here. So let's take a look. And we actually have a lot of symmetry here, right? Because, for example, the 4 corners, they are on equal footing. How many ways in this case cover, say, 1? Well, because the T-shape, the middle one and this one will never be able to use to cover 1. There's no way. So only the 2 corner ones will cover 1. So essentially what that means that if we have a 4 by 3 grid like this, how can we cover 1 here? Well, it can only be covered by this one. This is one way to cover it, or it can be covered by this way. Those are the only 2 ways to cover 1. Agree? This doesn't take too long to be verified. You cannot just cover this in any other way. So 1, this cell will be covered twice. Only 2. But 1 is symmetric to 3 and 10 and 12. So therefore, each of those 4 cells will be covered exactly twice. So now we know we can do 1 plus 3 plus 10 plus 12. They will be covered twice. Those 4 are in the same situation. Okay, that covers that. Now we have to consider, say, this one. This particular one. How many ways to cover this? You have to be careful to make sure that you count everything, right? So this is already one way, just like the first one. This is already T-shape cover this one. Is there any other way? Yeah, we can flip it, right? So we can also take this way to cover it, right? This is another way. Any other way? Yes, we can cover it this way, right? Because now it will be used by that. And by symmetry, we can, of course, cover it this way. So altogether, we already got 4 times different ways to cover this one. Is there anything else? I guess not. I really don't see any other ways of covering this. So we know this one, this is essentially 2, will be covered by 4 ways. And what is this number? It's 2. But 2 is the same as 11. So 2 and 11 will be covered 4 times. And so on. Okay? So if you say for this one, 4, 6, and 7, 9, they are all symmetric, right? The symmetry is right there. The symmetrical nature determines that you don't have to do all of them. You just do 1, say 4, then 6 and 7 and 9 are symmetrical in the sense that you can rotate different, they're equal. So what is that? Well, you just do, probably you will do a little bit more. The way I count is this can be either this one or this one. One for looks like you have more ways than this one. Yes, because in that case you can cover something like, let's just say 4. This is one way, right? But you can also shifting that by this one, and then oops, yeah, we are running out of time. So for this one, you can do a lot more. So this one, but you can also do this one, and you can also do this one. I believe there are 1, 2, 3, 4. It looks like you have 6 ways. Yeah, I think there are 6 ways, but that's unimportant. The important thing is that you will just follow this same process, right? And finally, this one and this one will be symmetrical. 5 and 8, they're in the same situation. So you just count each of those cases, then add them up. This is really an algorithm. You understand the nature of the problem, how to solve it. That's much more important than, of course, you still need to calculate it correctly as a matter of math competition, right? If you get the answer wrong, no matter how correct your algorithm is or your method is, still you don't get any point. But the problem is really give you an understanding of the nature of what we are doing here. We are trying to add up a group of numbers, and we try to figure out a way to correctly add them, understandable what we are doing, and do it quite efficiently. You just, in this way, we group the 4 times n method of numbers into 12 groups. What exactly each group means is that for each of the 12 cells, we count how many ways this cell will be covered. Okay? And the nice thing is that because of the symmetrical nature of some of those cells, we actually don't need to do 12 times. We actually do 1 group, 2 groups, 1 to 4 groups. Okay? And that will really speed up the process. But some cases are easy, and I believe the centers has the most cases. Probably should have probably still 6, maybe could be more than that. I don't remember the answer. You can check the solution, but the idea is quite clear. Okay, we are significantly over time, but you get the point. I will see you next time. Bye.